Hi there, this is Professor Shannon Gracie, and we are on section 11.1 in the Precalculus Enhanced with Graphing Utilities by Sullivan and Sullivan. So let's go ahead and get it started. Today we're reviewing systems of two linear equations and two unknowns, and we are going into systems of three equations, three unknowns. So it's going to be a pretty long section. So feel free to pause the movie and come back to it if you need to. All right. So here's all the stuff we're going to be doing, and let's warm it on up. All right. So go ahead, pause the movie, and see how you do on this one. Okay, so for this one, using the graphing calculator, we're going to need to isolate y in each of the equations. So 5x plus 3y equal to 21. We would have 3y is equal to negative 5x plus 21, subtracting 5x from both sides, and then dividing both sides by 3. Don't forget to divide both parts of the right side by 3. We'll get negative 5x over 3 plus 7. And for the second equation, negative x plus 2y is equal to 0. Adding x to both sides, we'll get 2y is equal to x. Dividing by 2, we'll get y is equal to x over 2. So now let's pull out our graphing calculator and see how we do. Okay, so for y1, we will have negative 5 times x divided by 3 plus 7. And then for y2, we'll have x divided by 2. All right. So now what we're going to want to find is we're going to want to find the point of intersection here. So let's just go to second calculate value. Oops, I'm sorry. Second calculate intersection. So we're on our first one, so hit enter, 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 and there's our intersection point. So let's do this kind of as a two-parter. Put our graph right here. So our point of intersection is right here. And the ordered pair is given below. It's the ordered pair, I don't know, let's go to the nearest hundredth. So approximately 3.23, comma 1.62. Whoops. All right, so we'll just rewrite it over here. And then what math problem have we solved? Well, I'm not sure if you remember way back when. You might have had these all the way back in introductory algebra. But basically, we've solved the problem. If you look at our original equations, we have 5x plus 3y is 21. And then we had negative, I think it was negative x plus 2y is equal to 0. So what we have there is a system of linear equations. Sometimes people put a comma after the first equation. Your textbook uses this this kind of notation to note a system. And so that's the system you just solved by graphing. All right. All right, so moving right along, we've got systems of linear equations and their solutions. So we've seen that all equations in the form of ax plus by equal to c are straight lines when graphed. Two such equations are called a system of linear equations, and actually it doesn't have to be two, it just really has to be more than one. Why don't we say two or more such equations? I don't want to do that. Sorry. We'll end up having a longer one for the systems of three equations. So they're called a system of linear equations, or just a linear system is fine. A solution to a system of two linear equations and two variables is an ordered pair that satisfies both equations. In the system. So when you move on to a system of three equations, three unknowns, you're in three dimensions and you end up getting an ordered triple instead of an ordered pair. But really the same, concepts apply. They're just a little more complicated. Okay, so first example, let's determine whether the given ordered pair is a solution of the system. So all you got to do is check each one. So 6 times negative 2 minus 2 times negative 5, is that equal to negative 2? Well, negative 12 plus 10, is that equal to negative 2? Negative 2 equals negative 2, so the first line checks out. So what we have ascertained is that that ordered pair is on the first line. Now let's look at the second line and check that one out. So we're going to check the same ordered pair, but in the second line. All right, so we'll get negative 6 plus, actually minus 5. Is that equal to negative 11? Negative 11 sure equals negative 11, so that checks out. So we would say yes, because it works. The ordered pair is a solution to both lines. Okay, so on to the next one. The ordered pair 10, 7. So checking the first guy, 6 times 10 minus 5 times 7, is that equal to 25? 60 minus 35, is that equal to 25? 25 equals 25, so the first one checks out. So then let's try the second one. 4 times 10 plus 15 times 7, is that equal to 13? Well, 40 plus 105, is that equal to 13? I think you can see that it's not. 145 is not equal to 13, so it fails, so we would say no. Even though it worked for the first line, it didn't work for the second line, so the ordered pair is not a solution to the system. All right, so solving linear systems by graphing. The solution of a system of linear equations consists of values for the variables that are solutions of each equation in the system. To solve a system means to find all solutions of the system. So when you're dealing with two equations with two variables, these are the types of solutions that you can get. So this one here, they're parallel lines. These guys will never intersect. So this is, your solution would be either the null set written like that, or you could do empty set brackets. And this is considered an inconsistent system. Now over here, when you have intersecting lines, you get an ordered pair solution, right? So you end up with just a single ordered pair, and this system is, both of these actually are consistent systems. This one right over here has independent equations. Because they're two different equations, but this one, a coincident line, also coincident lines also called collinear. This guy is, I think it's all one word. I'm spacing out today, guys. Collinear. So this one, basically, these lines are multiples of each other. So there's two lines that simplified when you got them in slope-intercept form to be the same line. So here, basically, you end up with an ordered pair solution, and you just write one of the lines in the system. All right, so three equations, three variables. A little crazier, you know. You can get here, the first one is a consistent system. It has a single ordered triple, an ordered triple solution. So this guy has an XYZ solution. That's the only spot that these three planes now intersect. And it is a consistent system. Now the one below is also consistent. These two here, these guys are considered to be coplanar. And so the planes are multiples of each other. And this guy, these are also consistent. And this one, basically with this one, it's not coplanar. They're not all the same plane, but they intersect in a line, right? They intersect in a line. So you basically would have a solution where you'd have x, y, z such that, and then you'd have x equal to something in terms of another variable, y equal to something in terms of another variable, and then we'll say this time z would be any real number. Oh. All right, so those are a little bit more complicated, but still doable. Now these up here, they're inconsistent, as you see here. There's no simultaneous solutions. So two of them might intersect, like you might have an intersection with two or three of them, but there's no single point or plane where they all intersect. And sometimes they don't intersect at all. They're horizontal planes. So think of three magic carpets, riding at different levels of the sky. All right, so let's check out what we have. So let's use this graph to figure out the solution of the system. So what do you think? Don't worry about the lines right there, the graph. Don't worry about this stuff right here. You're just focused on what? Good. You want to know where they intersect. These lines intersect where? At when x is -1 and when y is, great, -5. And so this is a consistent system with independent equations. All right, so you can also yield a graph like that on your graphing calculator like we did in the warm-up. So rules for obtaining an equivalent system of equations. You can interchange any two equations. You can multiply or divide each side of an equation, so you don't have to do it to every equation in the system. And you can do this by the same non-zero constant. And you can replace any equation in the system by the sum or difference of that equation and a non-zero multiple of any other equation in the system. All right? So let's start off with doing some systems where we have two equations and two unknowns. And in these, we're asked to solve them using substitution. On the, when we get to the exam on this, you can solve either by substitution or it's either called addition or elimination. Those are both, your author uses the word elimination method. You can check your work using your graphing calculator, all right? But I'll need to see the work you're about to see. Okay, so what I like to do is I like to name these lines in the system. So this system, we could call this equation A and this equation B. And we want to substitute, use the substitution method. So what you do is you pick the variable that's easiest to isolate. And I'm looking at equation B, and I'm thinking that we should isolate which variable you think? Great, y in equation B. So let's do it. So we have 3x minus y equals -14. Negative y, if I subtract 3x from both sides, is equal to -3x minus 14. Now if I multiply both sides by -1 or divide by -1, every term turns positive. Okay? So now I've isolated y. So next up, when you're doing a substitution, what you need to do is you need to substitute what you found into the other equation, one of the other equations. So we're going to say into equation A. And this is going to allow us to solve for x. So let's do it. So we have, let's figure out our equation A first of all. 5x plus 2y is -5. And we're going to basically take what we found for y and substitute that in. So 5x plus 2 times 3x plus 14 is equal to negative 5. So I just took what I found for y, which was 3x plus 14, and I plugged it right in there. So then we'll get 5x plus 6x plus 28 is equal to negative 5. I just distributed the 2 through, which will give us 11x is equal to, taking away 28 from both sides, we'll get negative 33. And then dividing both sides by 11, we'll get x is negative 3. So now we still need to find y. So here we go. Coming back here, we're going to substitute x equal to negative 3 into equation. You can do it to either equation. Why don't we just do equation A? And this is going to allow us to solve for y. So we have 5x plus 2y was negative 5. So 5 times negative 3 plus 2y is negative 5. So in for x, I put the negative 3 we'd found from the last step. And then we'll have negative 15 plus 2y is negative 5. 2y, when I add 15 to both sides, will be 10. So y will be 5. So now we'll do our conclusion. So this will be, what step are we on for? Conclusion. So what did we find? We found an ordered pair. So we found the ordered pair, negative 3, 5. And this system is consistent because we found an ordered pair solution. So it's a consistent system with independent equations because we didn't end up getting an identity statement. Independent equations. All right, how are we doing so far? Okay, so let's go on to this guy. The nice thing about this problem is y is already isolated. So if we call this equation A and this equation B, it's just your choice. Basically, y is equal to each of those things. So what we can do is we can set A equal to B. And that's going to allow us to solve for x. So here we go. Actually, it's not quite setting A equal to B. We're going to actually be, let's just do this. Substitute y equal to 5x minus 3 into equation B. And we'll be able to solve for x. All right, so here we go. So you have y is equal to 2x minus 21 fifths. And for y, we're going to put 5x minus 3 is equal to 2x minus 21 fifths. So that's what we did here. So let's see. Subtracting 2x from both sides, we'll get 3x is equal to negative 21 fifths plus 3. Need to get a common denominator, so if I multiply by 5 over 5, we'll have 3x is equal to negative 21 plus 15 all over 5. So 3x is, what is that, negative 6/5. And then if you multiply both sides by 1/3, we'll get x is equal to, we can divide out part of that, negative 2/5. All right, so far? Good. So now, second step, we'll have substitute x equals negative 2/5 into either equation. So actually, I think B will be the easiest since it already has the fraction. So we're going to substitute it into equation B. So equation B was y equals 2x minus 21/5. So plugging in x is negative 2/5, we'll have 2 times negative 2/5 minus 21/5. So this is what we did for x. We plugged in negative 2/5. So we'll have y is equal to negative 4 minus 21 all over 5. So y is negative 25/5, which gives us y is negative 5. So our conclusion will be, let's see, we're running out of space here, aren't we? Whoops. So our conclusion, we'll just put at the bottom here. So 3, conclusion. So we got an ordered pair solution of negative 2/5 and negative 5. And this is a consistent system since we got an ordered pair solution. And it was not the same line, so with independent equations. Oh, that got a little loopy, didn't it? Okay, so there's our result for that guy. Okay, so this one, again, we have our A and our B. So I think in this one, it'll be easiest to isolate x. So let's start off with that. We're going to isolate x in equation A. So we'll have negative x plus 3y is equal to 4. Negative x is 4 minus 3y. Multiplying both sides by negative 1, it'll flip the signs on everything. So we'll get negative 4 plus 3y. So now what we need to do is we need to substitute x equals negative 4 plus 3y into equation B. So you have to make sure you do it in the other equation. So equation B is 2x minus 6y is equal to negative 8. Whoops. So we'll have 2 times negative 4 plus 3y minus 6y is negative 8. So, and for this x, I plugged in this expression. So this will give us negative 8 plus 6y minus 6y is equal to negative 8. So this one's a little tricky. The 6y's zero out, and you end up getting negative 8 is equal to negative 8. So what do you think about this? If you look carefully, you'll see that equation B is equation A multiplied by 2. Do you see that? So they're actually collinear. They're the same line. So, or coincidence lines. So if you get this is a true statement. So what that means is there's infinitely many solutions. So what we have is X and Y such that, let's see, make sure your author answers them the same way, because sometimes they put it all in one happy ordered pair and sometimes they do not. So yes. So basically what we're going to need to do is this. We're going to need to solve for one of the equations. So if you go up here, do you see how we already had x equals negative 4 plus 3y? So this is what we're going to do. We're going to say x is negative 4 plus 3y, and then y is any real number. Okay? Because these guys are, and let's also put, we're doing our conclusion here. So if we had gotten something that was false, these would have been inconsistent. But negative 8 is equal to negative 8. So it is considered to be a consistent system with dependent equations because they're collinear. Okay? All right, so next up is the elimination method, So with the elimination method, basically you add multiples of the equations together and you end up getting the results. So what you want is for whichever variable that you decide to eliminate in the first equation, you must have the variable with opposite coefficient in the second one. So do you see here we have our equations, A and B. And do you see that the x's each have a coefficient of positive 1. So if I added them, I wouldn't zero them out. But the y's have coefficient positive 1 and negative 1. So if I add these two together, so I'm literally adding the equations A plus B, I'm going to eliminate y. So we'll have and then we add them and we get 2x is equal to 4, and dividing by 2 we get x is 2. Isn't that super awesome? And then our second step is going to be to substitute x equal to 2 into whichever equation you want. Let's just do equation A. So we have x plus y is equal to 6. We got 2 for x, so 2 plus y is equal to 6. Y is equal to 4. So x was 2. So now let's go for our conclusion. So we'll have the ordered pair 2, 4, and this is a consistent system with independent equations. All right, so let's see what fun stuff we have up next. Oh boy. All right, so here we go. With this system here, we have, I think the easiest way to adapt it is going to be, well, what do you guys think? Tell me what you think. Yeah, that's what I was thinking. I was thinking 5 times equation A plus equation B, and that will eliminate our y's again. So just a little side work. I'm not going to do this for everything, but 5 times equation A means I'm multiplying both sides of equation A times 5. So we would get 15x minus 5y is 55. Are we good there? So let's put that in. Oops, get my blue. 15x minus 5y equals 55. And then notice we'll have opposing signs on our y and opposing 5s on our y as coefficients to our y's. And that's what we were after. So adding, we'll get 13x is equal to 68. And dividing, we'll get 68/13. And I think that is, that's good there. So now our next step will be substitute x equals 68/13 into equation. So which one should we do? Let's just do A because the y has a coefficient of 1 there. So we'll have 3x minus y is 11. So 3 times 68/13 minus y is 11. And that was our x value we substituted in. So 3 times 68 is what? 24. 3 times 6 is 18. So I think 204. Does that look okay? Yeah. And then that's over 13 minus y is 11. So negative y is 11 minus 204/13. And we need to multiply 11 by 13 over 13 to get a common denominator. And get our calculator. So our 11 times 13 is 143. So negative y is 143 minus 204 all over 13. And then when I multiply through by negative 1 and complete, well, I'll say negative y equals for this one. So we'll have what? 4 minus 3 is 1. Negative 61/13. So that gives us that y is positive 61/13. So let's go to our conclusion. So we have the ordered pair 68/13 and 61/13. This is a consistent system with independent equations. All right, so let's see what we have going on with part C. So let's do it. So our first part, if we have this going on, why don't we do equation A and then minus 2 times equation B. That's going to allow us, no, you know what, the easier one this time, do you guys see, is going to be eliminating the x maybe. Either way, so A minus 2 times B, we'll say eliminate x. So what are we going to have? Negative 2 times B is negative 4x plus 2y is equal to negative 2. So the first one we left alone. And the second one we're going to write as negative 4x plus 2y is equal to negative 2. So let's see, we have 0 plus 0 is 0. 0 does equal to 0, right? So that's a true statement. So that means that we have one of those weird solutions going on. So here we go. This is our conclusion. So you end up with the ordered pair x comma y such that this point has to lie on one of the lines because they're both the same line. So I'm just going to pick the top line. And if you notice, and x and y are both real numbers. So if you notice, oh, actually that's what they did in this one, huh? Sorry. If you went ahead and if you isolate y, so in the, let's isolate y to set up our conclusion in equation B. And that would give us negative y is equal to negative 2x plus 1. So y is positive 2x minus 1. So that's what we'll put up here. We'll say y is equal to 2x minus 1, and x is any real number. Okay? All right, so this one has 3 equations, 3 unknowns. So we're getting into the big kid stuff now. So for this guy, let's go ahead and start with naming our equations again. We can name them A, B, and C. And you just have to make a judgment call on these. Sometimes using substitution the whole way through is good. Sometimes doing sort of half and half. Now, if you use elimination, what you have to make sure of is that you eliminate the same variable twice. Okay, otherwise you just get into this circular mess and you never leave the problem. When you have a funky problem like this, where one of the variables, different variables are missing from each of the equations. So what I would do is I would use substitution and basically substitute two different equations and write it in terms of each of them in terms of the same variable. So let's do it. So first off, I'm thinking that I'm going to isolate y in equation A, and I'm going to write it in terms of x. So when we do that, we have 2x plus y is equal to negative 4. So y will be equal to negative 2x minus 4. And then in equation B, I can only write y in terms of z. So I'm going to skip down to equation C, and I'm going to isolate y in equation C, because this way each y will be written in terms of x in each of them. Actually, sorry, Miss Gracie's making up her own math again. Isolate z in equation C, and that way it'll be a function of x, and we can substitute it back in to one of the earlier ones. So here we go. Equation C is 3x minus 2z is equal to negative 11. So we'll have negative 2z is equal to negative 3x minus 11. And then dividing both sides by negative 2. Remember, on the right side, divide through the negative 2 into both terms. So you'll have z is equal to 3x over 2 plus, actually, you know what? We don't need to separate it. We'll just keep it as one happy expression. But we will apply the negative. So it'll turn the numerator positive, and we'll have it just over 2. So this is what we got for z. So now let's look at it. Look at our thing here and see what we've got. So do you see that in equation B, if I plug in y and z as we found them, I'll just have an equation in x alone. So I'll be able to actually solve for x. So we're going to substitute what we found for y and z into equation B. And we'll be able to solve for x. So let's do it. We have negative 2y plus 4z is equal to 0. So what we got for y was negative 2x minus 4. And what we got for z was 3x plus 11 all over 2. So this was y, and this guy here was z. And all of that is going to be equal to 0. So I'll get 4x plus 8. This 2 divides out some of this 4, and then I distribute through and I get plus 6x plus 22 is equal to 0. So combining the x's, I get 10 x's, and the constants combine to be 30, and moving it to the other side, I get negative 30. Dividing by 10, I get x is negative 3. So now I can go back to A and C and plug in what I got for x and solve for them. So equation A, so substitute x equal to negative 3 into equation A. We'll be able to solve for y. So 2 times negative 3 plus y is negative 4. So we'll have negative 6 plus y is negative 4. So y is going to be 2. And this is what we plugged in for x. And then our fourth step will be, we're going to substitute x equals negative 3 into equation C. We'll be able to solve for z. So we have 3x minus 2z is negative 11. So 3 times negative 3 minus 2z is negative 11. 3 times negative 3 is negative 9. So we'll have negative 2z is, when I add 9 to both sides, I'll get negative 2. So z is negative 1. So we end up with an ordered triple. So our fifth step, sorry, I'll put it over here. Well, I don't want it quite over there. We'll do it over here. So 5, conclusion. We found an ordered triple, and x was negative 3, y was 2, and z was negative 1. So this is a consistent system. And it actually will have independent planes with independent planes. Okay? All right, so next up, we have this guy. So again, naming our equations. So this time what we're going to do is we're going to use elimination twice. So here's the strategy. Elimination twice. Just like, didn't we do that in the last one? Yeah, we'll get, or we used substitution maybe in the last one? I know it hasn't been that long. Let's see. Yes, so this one was a little odd. See, it had those missing variables, but this one we can do in a more in a different manner. So here we're going to decide what variable we want to eliminate, and we're going to eliminate it 2 times. So it doesn't matter what one chooses. I don't know. It looks like eliminating the variable y might be the easiest. So I'm going to add equation A plus equation, well, let's just do it. A and B and then A and C. Equation negative 3 times equation A plus equation B, and we're going to eliminate y. So here we go. Negative 3 times equation A is going to be what? Good, negative 3 times x minus y plus z is equal to negative 3 times negative 4. So we'll get negative 3x plus 3y minus 3z equals 12. And then equation B is 2x minus 3y plus 4z is equal to negative 15. So adding, we'll get negative x minus z equals negative 3. So now we're going to name this little equation D. And our next step will be to take equation A and add it with equation C and eliminate y again. So equation A was, what was it again? X minus y plus z is negative 4. And equation C is 5x plus y minus 2z is 12. So then, adding, we'll get 6x minus z equals 8. And we'll call this one equation E. So now what we've found, what we've gotten what we've accomplished is we have been able to reduce this to a system of two equations, two unknowns, the same two unknowns. So we're going to set up a system with D and E, right? So here, which one, I think it'll be easiest to eliminate Z if I multiply A, or if I, in D and E, if I multiply equation D by negative 1, I'll get positive Z in there. So that, I think, will be the best route. So negative D plus E, and we're going to eliminate Z, and we're going to be able to solve for X. Yay! Organization is truly the key in these. Oh, and I'm sorry, when we multiply, these will turn positive because D was all negative, so it's going to turn all positive. And then we'll have 6x minus z is 8. And when I add them, I'll get 7x is equal to 11. So I'll have x is 11 sevenths. Make sure I have that one correct. Okay. We can always check it at the end. Okay, so now what we're going to do is we're going to do here. Okay. Okay, so adding these, we'll have negative x plus z is equal to negative 3. So our next step is going to be we need to eliminate y again. So let's go check and see what we have. Whoops. So why don't we used a and b the first time. Why don't we go ahead and use a and c this time? And so and we won't need to make any adjustments at all. So we'll have a plus c, and we'll be able to eliminate y again. So a was x minus y plus z equals negative 4, and c is 5x plus y minus 2z is equal to 12. So adding, we'll have 6x minus z is equal to 8. And so let's name these new equations D and E, because see, now we have a system of two equations and the same two unknowns. So what we can do is for our next step, we can just add D plus E, because the Z's have opposing signs already. So that'll eliminate Z. So we'll have negative x plus z equals negative 3. And then we'll have 6x minus z equals 8. Let's see what we get. So we'll have 5x's is equal to 5, and dividing by 5, we get x is 1. Woohoo! We found an actual number. So on our fourth step, what we'll want to do is we'll want to take either D or E. Since we can see E really well, we're going to go ahead and substitute x equals 1 into equation E. We'll be able to solve for x. So equation E was 6x minus z equals 8. Plugging in 1 for x, we'll have 6 times 1 minus z is 8. Negative z will be 2. So positive z will be negative 2. Got 2 down, now just 1 to go. So now what we'll do is we'll substitute what we found for x and for z into, how about equation A? So what step were we on? 4. So now we'll be on 5. So we're going to substitute x equals 1 and z equal to negative 2 into equation A, and we'll be able to solve for y. So here we go. Equation A is x minus y plus z equals negative 4. We found x to be 1 and z was negative 2. And that's all equal to negative 4. So we're plugging in x is, whoops, wrong color. X is 1 and z is negative 2. And we'll get negative y. 1 plus negative 2 is negative 1, so negative y minus 1 is negative 4. Adding 1 to both sides, we'll get negative y is negative 3, and then y is positive 3. Okay. So we're ready to roll. We found our next step is our conclusion. So again, we found an ordered triple, and so we got 1, 3, and -2. This is a consistent system. With independent planes. All right. Okay, so let's leave it like this today. I think we've probably had enough work going on. So go ahead and do the parts of the problem sets that don't correspond to the applications, and you should be fine. All right, have a fabulous day. Bye.